This is our second lesson for Unit 4, and in this chapter, the first 4 lessons are all about using derivatives just to help interpret graphs, and we're going to do that in this lesson as well. And we're also going to look at this thing called the mean value theorem, just one of our theorems for calculus. Just tearing this apart, just looking at the words, kind of breaking it down into simple everyday language. This mean is not mean as in nasty, but mean as in average. And this value is actually talking about slope values, so, well, maybe I'll just write that as slope. And then theorem just means rule. So this is some sort of rule about average slope values. Every one of our theorems has this requirement that you have a function that is continuous. If it's not continuous, then none of our theorems are going to apply to it. And it has to be continuous on a nice closed interval from A to B. And this particular theorem has an extra little catch that it needs to have in order to be applied. It also has to be a smooth function, so it has to be differentiable. On that interval, but it doesn't have to be differentiable at the very edges of the interval. So you can actually have round brackets there, sort of soft edges are fine. And it says if you've got this function that is connected and smooth, then there's at least one x value, which we're going to call c, inside that interval such that this happens, right? And you kind of look at it and you're like, what is going on here? Well, actually, over here on the right-hand side, this is actually like a student in grade 10 just doing a grade 10 slope between a couple of points. So this is the average rate of change, the average slope. And over on that left-hand side, this is the derivative. This is good old Calculus 12. Okay, so this is going to be the slope of the tangent line. Okay, well, let's look at this just visually. It's actually easier to interpret what's going on. I want to imagine there's some function, and let's make it hit this point right here. In fact, let's call that a. That's where things are going to kind of begin, and that y value, we'll call it f of a. And let's finish at this point right here. That'll be where x is equal to b, and we'll call that y value f of b. All right, here's the plan. Take a ruler and go ahead and connect those 2 points with just a nice straight line, just like a student in grade 10 trying to find the slope between those 2 points. Okay, so that's going to be a secant line. That's when we're doing our average rate of change, and that's what this is all about. And now, here's the challenge. Try taking your pen or pencil and starting at this a, f of a, and finishing here, and try not to ever have the slope match that green line. You can't do it. It has to have the same slope as that at least once. And so I'm just going to go like this. I'm going to go way up and down and around like that. And there are actually multiple times for me where this is happening, where if I check out the slope of my tangent line, it's parallel to that secant line. Right? Here's another one, and here's another one again. Now, there won't always be 3, but there will be at least one time where that happens. And this theorem does nothing to try to help you find that place, you know, that spot right here where x is equal to c. It just says, well, it is actually out there. Now, I've only just taken a little small picture of that function. It could actually continue to the left and to the right, you know, beyond a and b. When it does actually continue, it doesn't have to be smooth, right? So I could actually have a cusp here, and I could have a cusp there. That's totally fine. It just has to be smooth inside that interval from A to B. Now, there are a couple of times where people go, oh, look, I found a counterexample. This mean value theorem doesn't always work. But they're usually, well, not usually, they will be violating the kind of terms of the agreement for the mean value theorem. So here's one where people would go, oh, yeah, I think I found a counterexample where it doesn't work. And it turns out they haven't really found anything. So I'm going to put my 2 points here, and I'm going to go and draw in my little grade 10 averaging line, and I'm going to try not to have my slope actually equal that. Well, maybe I have my function go like this, get to here, haven't quite equaled that slope yet, maybe I'll stop, jump down, maybe I'll jump down to here, and then make my way up like that and say, oh, look, nowhere did the blue graph actually share the same slope as the green one. Yeah, no kidding, but your function wasn't playing by the rules. It was not continuous. So if your function isn't continuous, well, then the mean value theorem doesn't necessarily apply. Here's another one. Again, we'll start here, going to finish there. Here's the average rate of change line, my secant line, that I might be like, oh yeah, I'm going to see if I can draw a function in blue that does not share the same slope as that ever. And oh, I saw my mistake on the left there. I accidentally drew one that wasn't continuous. Well, how about I go and do this? How about I go up to here, and then I'll go sideways like that. There. I never had the same slope as that green line. That's true, but that's not some big violation of the mean value theorem. It just doesn't even apply with the mean value theorem because that picture is not differentiable. It has a little hiccup right there in the middle of the graph. So I guess my point with those two little pictures there is this mean value theorem can only be guaranteed to work if you've got a beautiful function that is connected and smooth. Connected on the closed interval and smooth on that open interval on the inside. Now, you will in university talk about this thing called Rolle's theorem. It's actually just a little simple case of the mean value theorem. It's not part of the AP course, but you're going to see it at university, so we might as well talk about it. Now, I'm going to present it here as kind of a simplified special case of the mean value theorem. It turns out mathematicians started with Rolle's theorem and then worked from that to make the mean value theorem, but that doesn't really matter. Let's just talk about the theorem. This theorem says if one point is like this, down here at 0, and if the other point that you're going to work with is there, so here's your A and here's your B. So if f of A equals f of B, and if they're both actually equal to 0, then when you think about that averaging line between these 2 points, the slope's definitely going to be 0 for that grade 10 average rate of change calculation. And yeah, sure enough, your function's going to have at least one moment in there where you're going to find that the tangent line also has that slope of 0. And you might think, well, geez, why did you make the two y values for those blue points 0? You could have just made them level with each other. And yeah, I know, but this is the way Rolle's theorem actually works. So it says, yeah, there's going to be some spot C such that that derivative is actually equal to 0. So when you're talking about Rolle's theorem in university, that's all they're talking about. Now, before we flip the page, just going to go back up here. As we start to look at these theorems in the course, you're going to notice again that they all say your function has to be continuous. But this one's kind of extra special. Let me switch colors on that. This one's extra special because this one says, well, it only works with smooth functions. And our other theorems that we're going to look at don't have that extra part in there, but this one does. So it's kind of got tighter requirements just to get it to work. Okay, on the next page are some examples for using the mean value theorem. These are not easy theorems to use, and you have to be kind of really careful as you go and apply them. A lot of students find these a bit tough. Let's see if we can get this to work. The table on the right gives several values of the twice differentiable function. So when it says twice differentiable, what they're saying is that if you were to go and look at the derivative is perfectly happy. It exists all the time, so it's differentiable. And not only that, the second derivative is also a perfectly happy function that exists all the time. So this must be a really nice function. All right, is there any point where the slope of the function has to be 1.5 and then justify your answer? Let's do a quick little sketch over here just to see what's going on. I'm going to put my y values here, my f of x values, my x values there. And we've got these points, 2, 5, 8, and 10. So here's 2, and then we'll go 5, and then 8, and then 10. Okay, the points. I'm just going to roughly put these in here. At 2, we're at 1. At 5, we go up to 7. Okay, great, got that. At 8, we're going to be at 10. It's going to put us about here. And then at 10, we're going to be way down here at 4. All right. I don't know that the top of the function occurs at this 8, 10 point, right? The peak of the function could be up here. I have no idea what this function's doing. I just know that it's beautifully smooth. And they're saying, well, Do you think there's any moment where the derivative of the function that hits all those points has to be 1.5? And I would say that there is. I think there's definitely some point in there where that's going to happen. And here's what you have to notice. You have to actually pick off a couple of really interesting points in this table. I'm actually going to be grabbing this point right here and this point right there. I'm going to go from those 2 points. I'm going to add in my little grade 10 connecting average slope line here. I picked those two because I noticed something about the slope between them. So I had to sit there and play around with this table to try to find a place where I could get that slope of 1.5. Now, if I was justifying my answer, I would say this. I would say, well, you've told me that this graph is going to be continuous and differentiable. In fact, it's like twice differentiable. So it's definitely got to be continuous and differentiable. So the mean value theorem is a go, right? We can actually go ahead and use it. We needed that in order to be able to use it. Now, check out the slope between those 2 points, that average rate of change. If I go y2 minus y1, all on top of x2 minus x1, I end up with 9 over 6. I end up with that 1.5. So I searched around in the table until I could find that. And the mean value theorem tells me that somewhere, I'm not sure where, but somewhere between 2 and 8, this is going to happen. Okay, so there must exist some C, some special spot. And that C is actually in between 2 and 5. Could be at 2 or 5, but it's somewhere on that interval such that this is true. Such that the derivative there at that spot has to be 1.5. That's just the mean value theorem. So I'm not sure exactly where it is. You know, it could be anywhere kind of in here. Maybe it's, you know, somewhere around here where the graph, if I did actually draw this graph, it's like, oh yeah, right there, it shares the same slope as the green line. I don't really care where it is. I just know that it's got to be there somewhere in this space from 2 to 8, somewhere in here. Okay, part B says, is there a spot where the derivative is equal to 0? And I start looking at this table to try to find 2 points that I can connect and get a slope that's 0, and I just can't find one. But I could do this. I could say, hey, wait, hang on. What if I go and look and check out the slope, the average rate of change between those 2 points? Now, I know it's not 0, right? But let's kind of go with the same reasoning. And let's take a look at that average slope in there. So between 8 and 10, the average rate of change, y2 minus y1, all on top of x2 minus x1. That ends up being a negative 6 on top of a 2. That ends up being negative 3. So what I could tell you is there must exist some magical x value, right? There must exist a, well, let's move past C. Let's call it D. There must exist a D that's somewhere compressed in between 8 and 10, such that the derivative at D is equal to negative 3. And you're like, well, okay, that's great, but you were supposed to talk about how the derivative had to be 0. Well, let's just think about this graph here for a minute of the derivative. I don't even know what the function looks like, but I want to show you something I know about this graph for the derivative. So let's call this f prime of x, and here's x. And I know that there's going to be now some other spot, I don't know, somewhere in here, I'll call it D, right, snuck in there. Oh, I made a little mistake back here, actually. Looking back, this should not have been a 5. I think that should have been an 8. Not that it's going to much matter for where we're about to go. Okay, there is a place called C where if you go and check out the value of the derivative, I don't know where c is exactly, somewhere between 2 and 8. And if you check out the derivative, you're going to find that it's at 1.5. Right? That's what we proved up in part A. And then there's this other x value called d out here, where if you check out the derivative, it's now down here at -3. And it's like, okay, well, that's nice, but we were supposed to talk about whether or not this derivative ever had to hit 0. And the answer is, yeah, it's going to have to hit 0. If you think about it, this graph is going to have to make its way through that x-axis. We're going to have to hit every single y value at least once in between 1.5 and -3. That's actually a theorem we know already, the intermediate value theorem, right? The in-between y value theorem. So what I know is, if you're telling me that it's twice differentiable, right? That's what they said. If it's twice differentiable, then f prime must be continuous. So then you could just make a little note here and say, you know what? The intermediate value theorem, the in-between value theorem says we will hit every one of these y values. Okay, there's got to be some place, I don't know, what would we call it, E? It's going to happen. So the intermediate value theorem says there must be an x is equal to E such that f prime of E is equal to 0. In fact, there's another spot where it's equal to 1 and -2 and all the numbers in between 1.5 and -3 by our argument here. So these theorem questions can get a little technical, and you might sit there and go, well, look, I know it's true. But that's not good enough. You have to find some way to logically, carefully present your argument. And that's the whole kind of crux of the question is, can you put a nice, decent argument together? Not whether or not you know it's true, but can you prove to other people that it has to be true? Number 2, show that the function ln of x minus 1 satisfies the hypothesis, the preamble of the mean value theorem from 2 to 4, and then determine the value of c that's referred to by the theorem. Okay, well, let's take a look here. If that's the function, then the derivative, let's go and take a look at that. The derivative would be 1 over x minus 1. All right, that derivative needs to be working for us from 2 to 4. Now, this has an issue at x is equal to 1. Oh, no, we're nowhere near 1. We're going to work from 2 to 4, so we're totally okay. It looks to me like f is continuous because ln of x is, right, for this graph, as you move from 1 up. And also, I'm pretty comfortable now saying f is differentiable, at least on the section that we're looking at. Okay, at least on 2 to 4. So we're good to go. All right. The whole plan with this mean value theorem is that there should be some spot called C, where if you take the derivative there, it has to look just like the same value as what you get if you're in grade 10 just trying to find the slope between the 2 points. Well, we're trying to find that C, so it's like, okay, well, let's go and substitute C into this stuff I have here in green, C minus 1. There, I'm putting it into the derivative. Now, their stuff, what happens when we go and put in to this function? We're going to put in those two x values. 4 is the last one, 2 is the first. So we're going to have ln of 4 minus 1. We're going to have ln of 3, and then ln of 2 minus 1, ln of 1. Well, that's 0. Okay. So we just have to go and solve this. I think we can get there. We could say 1 all over c minus 1 is equal to ln of 3 all over 2. Okay, a little cross multiplying, and I think we can get this together. So we could say c minus 1 times ln of 3 is equal to 2. C ln 3 minus ln 3 is equal to 2. We're almost done. Just a little algebra here now. That's going to be ln 3 plus 2. All right, we found it. You know, the mean value theorem doesn't really tell you how to find it. It just says that it's out there. So we were kind of on our own here. We knew there would be an answer. And interestingly, this number C, it should be somewhere between 2 and 4, right? That's the whole idea. So I'm kind of curious. Just want to see how big that number actually is. We've got ln of 3, add 2, there's my numerator, divided by ln of 3. So this number should be somewhere sandwiched inside that interval from 2 to 4. Yep, 2.82. Okay, so everything's totally checking out. All right, what do we got? Another one here. I saw this one on an old AP exam, I think, somewhere. It says, okay, if f of x is a continuous function on an interval, and if f of a is equal to f of b is equal to 0, ooh, this kind of sort of sounds like Rolle's theorem here, right? Then what's happening? Let's try to do this one just by working backwards and just kind of seeing if we can do counterexamples along the way. So they're saying that the graph is 0 all the time, right? So if we did a little graph, I'm just going to sketch a little grid here. Give me just 1 second. Okay, let's put a quick little grid in here, and I'm just going to play around and kind of play like devil's advocate a little bit and see if I can come up with counterexamples to what they've got. So they're saying that f of a and f of b are both equal to 0. So that's like, yeah, you have to be here and you have to be there at a and b. Okay, so the part A says, oh, the graph has to be 0 the whole time. So they're saying if you look at the function, based on what they've said here, they said it was continuous, so you have to just draw that. No, I don't think so. I think it would be perfectly fine to do a graph that looks like that. That still meets this condition up there, so that's a no, right? You can scratch that one off. That's not true. Part B, the derivative might be different from 0 all the time. So it's saying it might never be 0. Well, I do know if I did a little grade 10 connecting line, you know, between these 2 points, that connecting line, that secant line, does actually have a slope of 0. And, you know, the mean value theorem, if we're using that here, would say, well, the graph's going to have a slope of 0 in there somewhere, right? And so it's tempting to say, yeah, if you think about it, you know, the mean value theorem is going to guarantee this little spot. And this is saying that, well, the derivative might be different from 0 the whole time. And I'm tempted to go, well, no, it's got to be 0 once. I'm tempted to scratch that off, but it turns out it's actually the right answer. And here's why. They said that the graph was continuous, but they never said that it was differentiable. So according to what they've got there, they're kind of tricking me here, right? Seeing if I would go, oh, mean value theorem. But I could actually draw this graph, and it meets their condition. It's continuous, and it hits those 2 black dots, and the derivative is never 0. So that's actually kind of a go for me right now, and I think it's going to end up being the right answer. But let's keep working away at this. So there does exist a number c in there such that the derivative is 0. Well, that's what the mean value theorem would say, but the mean value theorem doesn't apply here because it's not a differentiable function, so that goes. The derivative must exist the whole time. No, they never said so. It could look like that, right? So that doesn't have to be true. None of the above is true. Actually, I think B is true. So tricky one there. You know, what does it come down to? Well, in the end, be careful. You'd have to have continuity and differentiability before you could actually say, oh yeah, let's go ahead and use the mean value theorem. Okay, let's move away from the theorems for a bit, and let's try taking a look at functions. We're going to talk about whether they're increasing or decreasing. And it turns out we can do a beautiful description of that using calculus by using the first derivative. That's going to be our best friend to try to decide if something is increasing or decreasing. Now, key thing, when we go to do this description of increasing and decreasing, we're going to have to look at things from left to right. That's just the agreed upon direction. So I know if you were sketching this graph, you might actually take your pen And you might go, oh, I'm going to like draw my parabola like that. And you might go down with your pen both times. But if we're going to talk about mathematically whether it's increasing or decreasing, I have to start here and then go from left to right as I draw. And so that's going to force me to go up and then to go down. Okay, so let me just get rid of that. And a little emphasis here. So we are going to be moving from left to right. I don't care how you draw the picture, but that's how you have to talk about the picture. And what I can see is that, on this section here, if I'm moving from left to right, just a nice everyday language, I am going up. And as I look from left to right in here, looks like we're going to be going down. Okay, so some definitions. A function is increasing on an interval, and then there's this weird word here, IFF. That's actually a math abbreviation for if and only if. All definitions are always if and only ifs, right? They say, hey, this arrow goes both directions. So a theorem might have an arrow just going one way, but a definition, the arrow is double-headed and says these two things are interchangeable. So if you say a function is increasing on an interval, on a section of the number line, then this has to be true. If you were to check out the function at the first x value, you're going to find that it's lower than the function at the second x value. The second x value is bigger. And then this part here, where it says, oh yeah, well the x1 has to be less than x2, that little caveat right there, all that does is say, oh yeah, don't forget, we're moving from left to right. Okay, that's all that's in there for. So if I pick a couple of points, like these two blue ones here, 1, 1 and 3, 7, right? The 1, 1, that's my x1 point, and the 3, 7 is my x2 point. And yeah, 7 is better than 1, so that graph is increasing. And the interval here where we're going to go down, 6 is before 8 when you go from left to right, and then I can see these numbers dropping. And so here's my definition for decreasing. A function is decreasing if and only if. So again, it's one of those double-headed arrows. What we're about to write down mathematically is exactly the same thing as decreasing. And it's if when we check out these y values, that's what these are, right? These are y values. When we check them out, we have to see that we were bigger and then smaller. So that one's bigger than that one. Again, moving from left to right. That's all that this thing says. So increasing and decreasing is something that happens over an interval, happens over a section of the number line. What's interesting, and this is a bit of a technical issue, the AP markers have said we're not too worried about this, but it sure is cool to talk about. I'm going to add explicitly in here 1 point on this graph at 5, 9 right here. And we're going to have interesting discussions in class where we say, okay, where is this graph actually increasing? It's clearly increasing in here. And is it increasing all the way up to and including this 0.59? And the answer is, yeah, it is. Right? You can, if somebody says, well, what's the interval where it's increasing? You could go from here all the way up and you could actually include that last point. And somebody might go, well, it's flat there. How can it be increasing? And the answer is because to be increasing involves picking 2 points and then checking to see whether the graph is actually going up or going down for those 2 points. So you could pick like this point and that point. And if you're like, well, I don't want that point, can I go with this point here? Yeah, sure. You can even include that last point. And you'll find that those 2 orange points go up as you move from left to right. And likewise, it is also fair to say, when people ask you, well, where is it decreasing? You can actually use this point and then go down the graph like this and say everywhere on that pink interval. You can even include that point again, even though we included it in the description of where it was increasing. And it's okay to do that even though it's flat there because I picked 2 points. And I can pick this point and I can even pick that point if I want. And I would check and go, yep, those orange points are going down. So to be increasing or decreasing is something that happens over an interval. where you're picking 2 points. Now, we need to find some way to do quick rapid tests with calculus to see whether graphs happen to be increasing or decreasing. And so here is a nice little test that's going to work really, really well for us. As long as you're playing with a graph that is continuous, we want it to be connected. On the interval, oops, that was a really bad looking bracket. Let's try that again. Closed interval, hard edges from A to B. And if it's smooth, okay, if it's differentiable, on the interval A to B soft edges, that's good enough. I don't really care about the edges. Then here's how you can see whether a function is increasing. So this table's a little messy here. Let me just split this up here a bit. And we'll split this up here a bit. Okay. So number one, if you want to do a quick little test to see whether a function happens to be increasing, here is a way to know that it's increasing. If the derivative, when you check it out, if f prime of x, if it's positive, if it's greater than 0 for all of the x inside that interval, okay, so if all of this is true, right, if you're like, oh yeah, look, the derivative has been positive, that whole section of the number line, then, so this doesn't look like an if and only if, right, this is a then, so it's a single-headed arrow. If the derivative is always positive, then you know the graph has been increasing on that interval. It doesn't go the other way. You can say, well, hang on, could it be increasing and does the derivative have to always be positive? And the answer is actually no, because you could have a graph that's going up, hits a flat spot, and then goes up again. And we would actually say that whole pink line that I've drawn is increasing, even at that flat spot, because you always pick 2 points. So be careful, this does only go one way. If you say it's increasing, it doesn't always mean that forever, the whole time, that the derivative is positive. But the other way around does work. If the derivative is positive, then we know that the graph is increasing. And the reverse. If you want to do some sort of test to be able to say, hey, f of x is decreasing on some interval, I want to be able to state that, right? So these are my statements I want to make. Well, if you go and check out the derivative, and if the derivative is always negative, you know, for all of the x inside that interval, then for sure this graph will be decreasing. It is a one-directional arrow, though. Just to know that it's decreasing doesn't guarantee that the derivative is always negative. There might be one little flat spot in there. So that's going to be a super useful little test that we can use when we start to do some of our graphing. All right, one more bit of theory on the next page, and then we're going to try some graphs out. So how do you find some nice little local extremes analytically? We kind of looked at how you can do absolutes last day. Check out all the critical points, check out the endpoints, just find the best one. But what if you just want to find local ones as well? Well, here's one way to do it. Okay, it's called the first derivative test, and it's one of 2 different ways that we'll be able to test for local maximums and local minimums, local extremes. And we'll see another one that uses the second derivative, but this one's probably our favorite. It says if f of x is a continuous function with a critical point at x is equal to c. Okay, let's go over what that means. So to say that it's got a critical point at x is equal to c, then that means that at that spot, if you were to go and check out the derivative at that place, it's got to be one of these 2 things. It's got to either be 0 or it's got to be busted. So if you've got some critical point located at C, then if the derivative changes from positive to negative at x is equal to c, well, let's think about what that would look like. So I have a positive derivative and then some sort of critical point and then a negative derivative. That's going to be the top of a hill. Then you can say f of x has a local max. At x is equal to c. It might even be the absolute max, who knows. The reverse, if your derivative changes from negative derivative, a graph that's going to be pointing down, to a positive derivative, and it does it at that critical point, then at that spot, f of x has a local minimum, or you could say a relative minimum. I just don't have enough room to write that in. At x is equal to c. That's how we're going to verify or justify that we found a maximum. We're going to say, did you notice what the derivative did? It went from positive to negative right at that spot there, and it was a nice continuous function, so it's got to have a nice little peak to it. A little thought about the AP exam, okay, and how the AP exam is going to be marked. You have to mention that the derivative, that y prime, changes from positive to negative. I'm assuming you're trying to talk about a maximum. The other way around if it's a min. Okay, you have to mention that it does that, and then you have to say, oh yeah, look, it happened at x is equal to c. You have to own this question and say it's happening right here. Okay, so that x is equal to business, that's the place where the maximum is located. And again, I'm assuming we're doing a maximum for now. Here's what I mean by that. It's not good enough on an AP exam if they say, can you justify that you've got a local maximum? You can't just say, well, yeah, the derivative changed from positive to negative. You have to say, well, the derivative changed from positive to negative at x is equal to 11, and you have to mention that it's happening at this one point you're trying to talk about. You can't just kind of parrot back the phrase, oh yeah, derivative changed from positive to negative. The other thing that is definitely not good enough, it is not good enough to say that y, the function, changes from increasing to decreasing. Even though that's true, their reason honestly is this. This is what they've told us. Kids in grade 5 could say that. We want you to say something elegant based on what you know from your calculus. So you have to talk about the derivative and how you saw it switch sign at that x value. One last little caution. The word it is not a good word in the AP world, not on an AP calculus exam. If you were to say, well, I know that, it is a maximum because I saw it change from positive to negative when it did what it did at that x value. They're going to go, what are you talking about? When you say it changed from positive to negative, are you talking about y or are you talking about y prime? And they will never mark that right. Okay, so avoid the it pronoun when you're doing that justification. Okay. Now we're going to try this out for a few examples. Remember what we were talking about in the last lesson. It's going to take 4 of these lessons to get to the point where you can do this perfectly every time. So, just be patient with yourself. Here's what we're trying to do for this one. Find intervals of increase and decrease and any local extremes, any local maximums for this function here. Now there is the little courtesy graph, so we can see that there's definitely something going on right there. But what if we didn't have that graph? We're going to use this thing called a sign chart to keep track of what's going on. And on the first row, I'm going to have all of my x values, interesting x values on the number line, just from that x-axis. And then I'm going to have, kind of out of order here, the derivative and then the original function. So here's what I would do. I would go ahead and take a derivative and say, okay, what's f prime? Well, they told me the function here, so the derivative would be negative 6x plus 4. And then I would ask myself, okay, are you ever equal to 0 or are you ever busted? Can I find a critical point? I'm just going to move that a little bit. Can I find a critical point based on that algebra, negative 6x plus 4? And the answer is yes and no. I can't find any place where it's broken, so this is a never. But I could make that equal to 0 if I went with x being 4/6, or if you wish, 2/3. So that's an interesting spot, right? And sure enough, that's the critical point, like right there at 2/3. So we're going to go and take our number line, we're going to take our whole x-axis here, and we're going to start splitting it up, right? So here's my number line, there's my x-axis, and we're going to start making cuts in it at any of these critical points. And I've only got one critical point, one critical cut that's going to happen right here at 2/3. So I'm going to go and put that up into my table. I'm going to say 2/3 is a cut for x. I have all of the number line before that, so if I'm thinking about the number line, there's all of the number line that's happening up until 2/3. What about all of this? And then there's the number line after it. So I'm just going to write that down in my table. I'm going to say, okay, I've got all the numbers in the world on the number line from -infinity up until just before 2/3, and then all the numbers after 2/3. One cut gives me two chunks of the number line. I know based on what I wrote down here that the derivative is equal to 0 when x is equal to 2/3. Okay, now let's go and test some points. Let's just go and try out some points that are inside these intervals. Think of any number you can that's in this section of the number line. Like, go with easy ones too, like maybe x equals 0. If you put 0 in for x, you're going to get 4. So that tells me that this derivative is going to be positive during that whole section of the number line. You can write positive, or if you want, you can keep things simple. You can just go like this, right? Now, after 2/3, let's pick any number out here, like, I don't know, 1. So I put a 1 in. -6 plus 4, that's negative. We got a negative derivative. Now, I don't want to say it. I don't want to say it's positive, right? The derivative is positive. And I know that if I've got a continuous function, and on that whole section of the number line, the derivative is positive, then the graph f is increasing. So let's use that idea here. We can say, all right, in that section of the number line, f is increasing. Don't scramble these two issues up. Don't tell me that f is positive or that f prime is increasing, right? That is not what you want to say here. And the f prime being negative in that whole section of the number line, that whole interval, that tells me that f is going to be a decreasing function there. All right, we have a critical point of 2/3, and the derivative switched from positive derivative to negative. That means that we definitely have a nice little local maximum happening right there at x is equal to 2/3. If I want, I can even go and find that value, okay, that local maximum value. I would go and substitute 2/3 back into f. And when you do that back into the original function, you get 7/3. All right, now how do you justify that you just found this is a local max? It's also the absolute max. But if they said, okay, well, justify that you've just found a nice little local max there, I would say, here's my justification. There is a local max at x is equal to 2/3. Okay, now I could just say because I know it, right? Yeah, sure, that's what you know, but how do you prove it? You haven't proved anything yet. Here comes the proof. Because. Now don't say the function switched from increasing to decreasing, because kids in grade 5 can do that. You have to say because f prime, because the derivative switches from positive to negative. And that is not good enough either, because they would say, well, where did it switch? You have to say, well, at 2/3. Okay, well, you should have said that then. And you must say this, at x is equal to 2/3. You have to own this question, right? And so that last line, that last little part right in here has to be there, right? That at x is equal to 2/3. Okay, let's try another one out here. These are going pretty easy here now. Let's try example 5. Find intervals of increase and decrease. And by the way, the table does that, right? So back here, there's my interval of increase and decrease. I don't think I need a sentence right now. And local extremes for this thing, this little cubic polynomial. Oh, and then also find absolute maximums and minimums in here. Yeah, sure. Okay. Well, let's go and do our usual game. Let's go and do a derivative. So I'm going to go and find my f prime. Going to do a derivative of that polynomial. It's pretty easy. I'm going to have 3x squared minus 18x plus 24. Now I'm going to need to know when that's equal to 0, so I'm going to factor this thing. I can extract a 3. And then this even factors some more. You're going to be factoring a lot, especially in this chapter. Okay, now I can go and answer the question. Are there any critical points here? You know, are there any times when that derivative is equal to one of these things? Is it equal to 0? That would be a flat graph. Or is the derivative broken? That would be a kink in the graph. And the answer is, yeah, we can make the derivative equal to 0 if x is equal to 2 or 4 on the number line. But you can't break that derivative. That's a never. We'll see some of those soon enough, but for now that's a never. Okay, that gives me 2 cuts on the number line at 2 and at 4. 2 cuts separates the number line into 3 pieces. I have the number line from minus infinity up to 2, between 2 and 4, and then after 4 out to forever. I want to figure out what's the derivative doing on those intervals in there before and between and after the 2 and 4. I know that the derivative is equal to 0 at 2 and 4, okay, but what's it doing before and after those moments? So you try a number out that's in this interval. You try a number out like 1, and you substitute it into here to see what is that derivative doing. And when you try that out, you'll see that you get a positive answer. So the derivative is positive. That tells me that the function is increasing. Okay, there's a little increasing interval for you. Then from 2 to 4, try a number like 3 out. You can put 3 in here. You'd have 3 times 1 times a negative 1. You're going to get a negative derivative all in there. That means the function is decreasing in there. And then try a number out like 5 into here. Just test it and you'll see that it's positive, which means that the function is increasing. Okay, so I found my intervals of increase and decrease. Now, you know, to be technical, if somebody said, well, what's the interval of decrease? If you said this answer, 2 to 4, round brackets, it'll get marked right, but you could even put square brackets on it, according to the official rigorous definition of decreasing. But I'm going to say the table's fine. Let's go and take a look at these points, though, to see if they're maximums or minimums. You know, we can use the little courtesy graph as a guide, but if we look, we can see this. The derivative switches from positive to negative, right? So the graph went from uphill to downhill. That is going to be a little local maximum. And then here the derivative switches negative to positive. That's going to be a local minimum. So I've done a lot of what they've asked for. I found intervals of increase and decrease. I found local extremes, but then they're like, ooh, can you do some absolutes on that interval with those endpoints? Sure. Here's what I do. This is back one lesson now. I would check out all the y values, including the endpoints. Check out what's happening at 1.5. Check out what's happening at 2, that first critical point. Check out what the y value is doing at 4. Check out what the y value is doing at the very end at 6. We do want to check even the endpoints, right? So be careful about those. Just abbreviating that because I don't have a lot of space. When you check out the y values, I'm just going to offer them to you. This is 9.125. This is a 10. This is a 6. And this is a 26. And so people are asking you, like, well, what's the absolute minimum? What's the absolute maximum? I can just look through this table and say that one there is your absolute minimum. And on this interval that we're talking about, that is the absolute or global maximum. So absolutes, we can just check. What are the best and worst y values that we see? But you got to check the endpoints as well. This graph was climbing like crazy by the time we got out to 6. All right, number 6. Intervals in increase and decrease, local extremes, no globals. Okay, so this will maybe go a little faster. All right, let's play our game. Let's go and do a derivative. So f prime, that's going to be, the 4 comes down, hits the quarter. Ooh, that's kind of nice. That's actually just going to be an x cubed. Okay, it looked like it would be hideous, but it's actually pretty nice. Minus a 6 x squared plus a 9x. I need to know when that thing is 0 or busted, so I'm going to start factoring this thing. I can extract an x, and then I have x squared minus 6x plus 9. Actually, this one's going to factor with a binomial squared. We're going to have x, and then we're going to have an x minus 3 in there twice. Sure, you can write that with a square, or you can write it like that. Okay, well, let's go and look for critical points. Right? The whole idea of critical points is asking, could that derivative be 0 or broken? Okay, so we're kind of wondering, critical points? So we're saying, could that derivative ever be 0? Could it be busted? Well, I can make it 0 by making x either equal to 0 or 3, but I cannot break this one. Don't worry, there will be many coming up that do get broken, but not these ones, not these polynomials. Okay, 2 cuts to your number line, 0 and 3. Remember, this first row is going to be your x's. So we have got all of the x's before the 0, all of the x's in between 0 and 3, and then all of the x's from 3 out to forever. I want to try to figure out what's happening with the derivative on those in-between times. I know that the derivative is 0 at 0 and at 0 at 3. That's all very nice. But what's it doing before 0 or between 0 and 3? So you try numbers out. You try like a -1, and you can put it into this blue stuff anywhere, whatever line you like. Put that -1 testing x value in, and you'll see that the derivative is negative. So the function is decreasing. And then you try a number out between 0 and 3, like try out 1. And if you do, you'll see that in this interval, the derivative is positive. So the graph is increasing. Okay, notice I didn't say it. The derivative is positive, the graph is increasing. Then you try out a number like 4, and you find that, well, it's actually positive again. You might have expected it to go negative, to flip-flop, but it doesn't. So the derivative is positive, which means the graph has gone back to increasing. So do we have any local maximums or minimums? Well, there's one here. The derivative switched from negative to positive. That's going to be a minimum. But here it didn't actually switch. So it's not a max or a min. It's a special little point. I like to call them decoys because it's like right here and it's like, I'm going to be a maximum. And it goes, fooled ya. It's actually got another name we'll see in another day called an inflection point. And then there's this local minimum right there. So we found a local minimum. That's about all we found. You can actually go and find the value for that if you really wanted to. You could say, oh, I got to find that minimum value. Yeah, just go and put the 0 in. Turns out it's a 1. Right? So there's your local minimum value of 1. Now, I do want to just highlight this issue of maybe writing answers down here now. So if they said, hey, where's this graph decreasing? If you were to say, well, negative infinity, 0, round brackets, that'd be okay, but you can actually be a little more aggressive. You can say from negative infinity up to 0, hard edge, and you can even include the 0. And I'm going to include that 0 when I go and talk about increasing. So if I was formally writing down my answer for, hey, here's my interval of increasing, I would say you can start at 0, because you pick any 2 points and you'll see that as you move from left to right, the points go up. And I don't even have to stop at 3 and then restart. I can say, you know what, just go right on out to infinity. That's fine. Because I don't mind the 3 being in there, because if you pick 2 points on that interval, again, you will see things are actually growing. Okay, we're going to do one more page, just 2 more examples here. Find intervals of increase and decrease, any local extremes for this thing. I'm going to rewrite this. I don't like the way that function's been written there with the root sign. I think we can maybe write it a couple of different ways. We could write it either like this, x to the 2/3, right? We can do that. And by the way, this could also be rewritten here as the cube root of x all squared, right? Same thing. But I'm going to go with that power up there in the top. Okay, time to do a derivative. See what happens here. So the derivative for this thing, treating that as a power, I'm going to have 2/3 x to the -1/3. All right, that's great, but I really want to stare at this thing to try to figure out, like, when is it 0, when is it broken? So it is worth tidying this up a little bit. I know we didn't in the last chapter, but here it's useful. So this is a 2 sitting on top of a 3, and then there's this cube root of x down in the bottom, like that. Okay, well now we can answer the question. Is there a critical point anywhere? Are there any places where that is equal to 0 or that's broken? Well, you'll make a fraction equal to 0 if the top is 0. You can't do that because it's busy being 2. So that is a never. But you can make the fraction does not exist by making the bottom 0. That'll happen when x is equal to 0. So that's the critical point. That deserves a slice in your number line, right? Remember, this row here, these are the x's. And yeah, sure enough, I can see that there's a critical point here, right? There's no tangent there, but it's definitely an interesting point. And the graph is beautifully continuous. It's all connected. It's just not differentiable there. Okay, so that's going to slice up my number line. I've got all of the points up to just before 0, and then all of the points after 0 to forever. So now you try numbers out. Try a -1. Put a -1 in here. You can do the cube root of -1. Doesn't hurt anything. And you find that you get a negative answer. So the derivative is negative, which means the function is decreasing in that section. Then you try a number out like 1 in the derivative, in this blue stuff, and you see that the derivative is positive. That means that the function is increasing. Now, the derivative does not exist at that x is equal to 0. There is no derivative there, but the function exists there. And I'm noticing that the derivative at this critical point makes a switch from negative to positive at x is equal to 0. So that is definitely a local minimum. Right, so we found the local minimum. We're pretty much good to go. If you really wanted to know, well, what is the actual value, right? Sometimes people will want to know that. Then you could go and say, well, let's go and put that 0. Let's go and put that x value into f. And when you do that, that would be the cube root of 0 squared. So it's actually 0. So yeah, you've got this point 0, 0. Once again, if somebody said, well, what's the interval where it's increasing? I think the table here does a pretty decent job of saying, you want to talk about where the function is increasing? Yeah, here. But yeah, officially, if I was writing it down in a separate sentence, I could actually put a hard bracket, a closed bracket on that x is equal to 0. Not a big thing. We're not going to split hairs too much about that in AP Calculus. Last one. Got a little rational function here. It looks like a tree trunk, right, with that asymptote at x is equal to 1. And I want to rethink this. I want to try to avoid doing quotient rules if I can. They're not my favorite. So I'm going to think of this as x minus 1 all to the -2. All right, derivative f prime of x. Okay, little chain rule action. You're going to have a -2, x minus 1 to the -3 times a 1 from the chain rule. And I can rewrite that. Just clean this up here a little bit. Got a -2 up in the numerator. And then down on the bottom, we have an x minus 1 cubed. Okay, and I'm wondering, here's my usual game. Could I make that 0? Or could I make it does not exist? And the answer is, well, you can't make it 0. There's no way you can make that fraction equal to 0 because that top is busy being -2, so that's a full-on never. And sure enough, the graph is never flat. And the bottom being 0, yeah, that could be done. That could be done at x is equal to 1. So the graph's going to have an issue there. Turns out there isn't actually a critical point there because the graph doesn't even exist there. It's kind of interesting. But let's go up to our number line, make our one cut at x is equal to 1. We're going to have all of the x numbers. This is the x row. All the x numbers from minus infinity up until 1, and then all of the x numbers from 1 to forever. What I do know is that the derivative does not exist at 1, and the function does not exist at 1. Right? So nothing's happening there at 1. If I test a value, pick a number in here like 0, and try out this derivative, you'll find that the derivative is positive, meaning that the function is increasing in that section. And then you test a number like x equals 2 in this blue derivative, and you find that the derivative is negative, so the function must be decreasing on that interval. So we certainly have found the intervals of increase and decrease. Now, I did see the derivative switch from positive to negative, so I'm kind of tempted to say, ooh, a max. But this graph wasn't continuous there. So that rule of saying, hey, you know, if the derivative switches from plus to minus, going to have a max. Yeah, it's got to be continuous. This one is totally broken there. So this particular graph has no local max or min. And that's going to finish up this lesson.